last week we started Kubernetes and we stopped at trying to explain the concepts around Kubernetes. So I think we can use today to finish that up and see what we can do, right? So before I start up, do we have any questions maybe from the last class? Maybe during our practice we found out something that we wanted to ask or clarify. Anybody? Any questions?
No, I think we are fine.
All right. All right, can you see my screen?
Yes, screen is visible.
All right. So I was talking about the control plane on that day. I think that was where we stopped. Trying to explain the components of the master node. So we'll just continue from there and try and finish up. So I was talking about the master node, which is also called the control plane, which is the controller and manages the cluster and applications within the cluster. The master node is made up of various components, all having unique responsibilities to keep Kubernetes up and run and your applications within the cluster running always in good condition. These components are installed by default whenever you run the Kubernetes installation command and run as a daemon process within the master node. Now, the Kubernetes control plane is made up of these four major components. We have the API server, we have the etcd, we have the control manager, and we have the scheduler. The API server, etcd, control manager, and then the scheduler. Now, let's look at these four components individually. So the first one is the API server. Now, this is the server that receives requests from the CLI application, kubectl. kubectl is usually the application used to administer Kubernetes cluster. We'll get there very soon. And executes those commands accordingly. It can also receive direct API calls. So being the API server, it means that every request of what you want to do within the Kubernetes cluster happens from within the API server. API server is like the interface, okay, just where you have your AWS console on the AWS API. That's what the Kubernetes API server is. So it stands and faces the it stands like the face of the Kubernetes cluster to receive every single request on what to be done, what needs to be done. The next component we have here is called the etcd. The etcd serves as a database or memory storage for the Kubernetes cluster. It stores all configurations of systems and applications within the cluster. So you can call this the memory storage of the Kubernetes cluster, where all information configuration are stored within the Kubernetes cluster. The other component of the Kubernetes cluster is known as the control manager. This is the component that's responsible for most of the collectors that regulates the state of the cluster and performs tasks. You have the API server that receives requests. Now, when the API server receives requests, what actually performs the operation, that is the instruction given to the API server, is the control manager. So if it needs to terminate a container, if it needs to terminate a pod, if it needs to, any operation that needs to be done is done from or within the control manager. So it's more or less the brain box of Kubernetes cluster. The next we have here is called the scheduler. The scheduler is responsible for scheduling pods on the worker nodes in the cluster. So when we talk about scheduling pods, we're talking about where a particular container will be deployed. Now, we already established the fact that Kubernetes works in a cluster mode. What we mean by cluster mode is more than one EC2 instance or more than one virtual machine is needed to run a production grade Kubernetes cluster. Your Kubernetes cluster might not be production grade, might be on a single node, or it can be on multiple nodes. But for production grade Kubernetes cluster, it must be on at least 3 worker nodes. Okay? At least 3 worker nodes. So what the scheduler does, sorry, excuse me. Yeah, sorry for that break. So I was talking about etcd. I said this is, sorry, I was talking about the scheduler. So I said the scheduler is usually used to schedule work. Now what it means by scheduling work is deployment of a pod. Okay, a pod is the smallest unit of workload in a Kubernetes cluster. Please, are we together? Can you hear me?
Yes, we can.
Yes.
All right. So whenever you deploy a particular application in Kubernetes, it's usually called a pod. Okay. So the job of the scheduler is to decide which of the nodes within the cluster is going to deploy that pod to. Now, that's the job of the scheduler. It does it using certain logic and certain parameters to decide what that how that's going to be deployed. So the scheduler sits in the control plane, which is in the master node of the Kubernetes cluster. It's the one that decides where every pod is going to stay. Now, apart from the master node, we have what we call the worker nodes. Now, the Kubernetes worker node is where pods are deployed and where the application runs. It receives instruction from the master node. The worker node is also a virtual machine or an EC2 instance. So just like the master node, sorry, unlike the master node that can be a managed service that you don't have access to the master node, the worker node is quite different. It can be only an EC2 instance or a VM, although that is gradually changing. Now, you have serverless pods currently. So AWS Fargate is an example of a serverless pod. So it means that in the very soon, in the coming months or years, you can have serverless master node, and then you can have serverless worker node or serverless pod. So this time, we're not even looking at the worker node anymore. We're looking at the particular pod we're trying to deploy. So, but at this point in time, the worker node is what we are talking about. So the worker nodes are usually virtual machines or EC2 instances. Now, a worker node is made up of 3 major components. You have the kubelet, you have Docker, and then you have kubeproxy. You have the kubelet, you have Docker, then you have kubeproxy. Now, the kubelet is a daemon process that waits for instructions to perform tasks. Now, just the way we have the control plane and the API server receiving requests. Whenever everything is done, the Whenever you deploy a pod, the instruction gets to the API server. From the API server, it sends the instruction to the control manager where what needs to be done is decided based on certain parameters and then sent to the scheduler. So the scheduler is what determines which node within the cluster to deploy that pod into. Now, when it does that, it sends the instruction to the kubelet because the kubelet is a daemon process that runs across all the worker nodes within the cluster. So it's now the job of the kubelet to actually deploy that particular pod within that cluster or within that node where it needs to be deployed. The next thing you have here is the Docker, which is the runtime for the application container. So I use Docker as a runtime here. The runtime could be anything, basically. And then you have kubeproxy, which serves as the proxy within the cluster. So within a cluster, there are always network requests, okay, that happens to the cluster. So kubeproxy stands there to serve as the network proxy for requests coming into that worker node. So this is a clear diagram of what Kubernetes cluster looks like. I don't want us to briefly look at the diagram if there are any questions.
All good.
All right. So let's take a look at what we call Kubernetes objects and resources. Now, applications can be hosted in different configuration manner. Every deployment within Kubernetes is called the word kind. This statement defines how the application will operate within the cluster. Different objects have unique functionalities. I'll be looking at the most common kinds in Kubernetes and explain what they mean. Sorry for that break. Okay. So let's take a look at Kubernetes resources and objects. So the first one I'll talk about here is a node. So when you say a node in a Kubernetes cluster, what do you mean? So a node is a machine or a virtual machine in a cluster. A group of nodes make up a Kubernetes cluster. There is a master node and a worker node. Most clusters have a single master node and many worker nodes. But some scenarios for high availability, you can actually have multiple master nodes. So the whole idea is that whenever any master node has a problem, you can always switch over to the next master node. The next we have here is called a namespace. So a namespace is a logical separation of workloads within a Kubernetes cluster. A namespace makes it possible for you to deploy different kind of environment within one cluster. So let's say you want to have development, staging, and production. You can actually share your cluster into as many divisions as you want. So when you deploy a particular pod within a namespace, it has no business with any other pod in another namespace. So it creates a line of separation from the networking configuration to every other configuration where both pods do not communicate. So namespace is a very good way to actually draw a line between two deployments or two pods that we have within a cluster. Does that make sense to us?
Yes.
Well, the next component we have here is called a service. Now, a service is an abstraction on a pod that gives it an IP or a DNS name and allow it to receive traffic. Now, a pod on its own does not have any way to actually know or receive traffic. Okay, but you need to create a service and attach that service to the pod before it can actually receive traffic. So receiving traffic means that you can communicate with that particular application. So unlike the normal Docker, what happens is that you need to do a Docker run -p. That's where you bind a service to the container. But in Kubernetes, when you launch a pod, there is no connection to that pod. So what you need to do is to create a service layer that receives traffic that now sends it eventually to the pod. And that's what the service abstraction is about. The next one we have here is a pod. So a pod is the smallest unit of deployment in Kubernetes. What this means is that just the way you have containers, in Kubernetes, we don't call them containers, we call them pod. But within Kubernetes, actually, a container runs inside a pod. So when you deploy a Kubernetes cluster, what you have is actually, so when you deploy an application or a microservice within Kubernetes, what you have is actually a pod. And it is the pod that holds the application, your Docker image that has been deployed. So you can say a pod is a running container or a running image that you have run. Just the way when you run a container in normal Docker, when you do Docker run for an image, you run a container. In Kubernetes, it's called a pod. Now, the interesting thing about a pod in Kubernetes is that you can run multiple containers in a single pod, or you can run a single container in a single pod. Personally, I would advise people to run a single container in a single pod. Reason being that you are able to manage a single process per time instead of having multiple processes, which could actually be very detrimental or confusing to what you are trying to do. That's a mistake of repeating service and namespace. Next we have here is a replica set. Now, a replica set ensures a number of pods should be running. It is usually used for high availability. Now, what the replica set means is that you are able to replicate a pod into many copies. Now, at the beginning of this course, I talked about replica sets. So this is the explanation of a replica set clearly. When you build a Docker image and you deploy it into Kubernetes, it becomes a pod. Okay. Now, you can have just a single pod running at a particular point in time. But for production use and high availability, I mean, that is very unsafe because if anything happens to that pod, it means that your whole application is going to go down. The best way to actually protect your application from failure or single point of failure is to create a replica or to create a copy, which is what autoscaling does for you. So what you do with autoscaling is that you have 2-3 copies or more or less virtual machines that host your application. If anything happens to one node, you are able to get a new node via the autoscaling or a new EC2 instance in a replica set. Now, when you're configuring a replica set, you tell Kubernetes to create identically 3 pods for you, or 4 pods, or the number of pods you want. Personally, I usually advise that you have 3 pods, okay, for a production workload. So the advantage here is if anything happens to one pod, 2 pods are still standing. If anything happens to the other pod, 2 pods are still standing. So at every point in time, you're going to have 2 pods running, even if one pod has a problem. Okay, and also Kubernetes, we already established that Kubernetes does self-healing. So it means that it can actually recreate that pod. So the replica set just makes sure that your application has high availability, and you can have as many replica sets, means as many pods as you want. Now there's something called but there's some kind of limitation. There's something called pod capacity. Now every node within your cluster has a number of pods it can run. Now within AWS, it's quite easy because there's a calculation AWS has done that helps to make that easy to find out. I want to share a link that could help with that. Sorry, let me quickly get the link. Okay, it's a blog post I wrote. You can just check it out. So what I was trying to talk about here is actually how pod capacity works and how it affects your Kubernetes workload. Now, what does pod capacity mean? Now, every EC2 instance has a set of pods that it can run. at a particular point in time. So if you're not aware of pods, your nodes will run as I just share the link now. Did you guys get it? Did you get the link?
Yes, we
Hello.
get it.
All right. So what it means is every node, okay, which is more or less an EC2 instance, has the number of pods it can take, and there's a calculation for it. If you check that article, you will see the calculation for it. Now, if you are deploying your pods within your cluster, it's good you know the number of pods a node can take. Okay, because if you don't, you might get to an extent where you deploy and actually you will not be able to deploy any other pod anymore into that cluster. So even if you have a 3-node cluster, let's assume you have a 3-node cluster and each of the nodes can take 10 pods, okay? That means you have a total of 30 pods you can deploy in that cluster. If you have a lot of applications, let's assume each application you are making a replica set of 4. You'll notice that before you know it, you would have filled up all the nodes within that cluster. So there are two things you can do. The number of pods a node can take is usually proportionate to the size of the EC2 instance. So the higher you go with instances, the more pods you can take. So from T2 nano to T2 micro to T2 small, T2 medium, T2 large, as you go higher, the node will be able to take more pods. Okay, so that's just it, but there are other calculations, the network interface card and all to arrive at the actual figure. So it's very essential to know the number of the number of pods your node can take at any point in time. So just the way you can do replica sets, you also need to be aware that there is a limit to the number of replicas you can have, which is based on the number of pods your node can take. Is that clear enough?
Okay.
Okay.
All right, so the next thing I want to talk about here is deployments. Now, deployment represents a set of multiple identical pods with no unique identities. Now, a deployment is what you use to usually house your pod. Kubernetes allows you to deploy a pod as an individual component. It also allows you to deploy a pod within a deployment. Now, it's within a deployment that you can actually ensure that your pod has what you call high availability, or it can actually recover during a failure. So what happens when you deploy a pod within a deployment is the deployment tries to maintain the state of that particular pod. So if anything happens to a pod within the deployment will ensure that it recovers that pod, because you usually set the number of pods you want in your deployment. So that is also where you configure your replica sets. In a deployment, when you configure 3 pods, it means that you are saying you want a replica set of 3. Deployment will make sure that you have 3 pods at any point in time. That's the logic behind recovery. So if anything happens to any pod, the deployment is going to check and ensure that how many pods do we have at this point in time. If there's anything less than what was configured, it will make sure that it sets up or it tries to schedule a new pod within the cluster. So this is usually a communication between the kubelet, the scheduler, and the control manager. So if for example, you configured that you want your deployment to have 3 replica sets, that means 3 pods, okay? Now, if something happens to a single pod, what happens is the kubelet checks that deployment and says, how many pods do we have? If we have less than 3, which is 2, it's going to send a request to the control manager. The control manager we only have 3 pods here. Sorry, we only have 2 pods here, which should be 3 from the configuration, which is called an etcd. The control manager will immediately trigger the scheduler and say, scheduler, can you create a new pod in one of the nodes? We actually don't have enough pods. And the scheduler goes on to also tell the kubelets, okay, create this particular pod with these configurations, which is maybe the Docker image, the configurations, the secrets, and every other configuration that comes with it. And with that, you can now have that particular pod recreated in that node. Am I making sense? Is anybody there?
Can you please repeat the number of ports will be the scheduler will further?
What I said is when you are trying to set up a deployment, you can actually configure the number of pods you want at a time. And it is the job of the kubelet to ensure that whatever you configure is always what is there. So what it means is that if, for example, you have 3 pods, okay, and anything happens to one of the pods, let's assume it's an application bug and the pod fails or it stops running, or the container stops running and the pod fails, the kubelet will communicate with the control manager because the kubelet has constant communication with the control manager. When it communicates with the control manager, that same information, it decides and finds out that there's no pod. It sends the request back to the scheduler because the scheduler that ensures that pods are deployed. The scheduler starts to deploy a pod and tells the kubelet to deploy a particular pod so that it can continue to maintain the state of 3 pods within that deployment.
Okay.
And also take note, your pod can actually be on any of these C2 instances or any of the worker nodes. So if you have 3 nodes, a single pod can be on node 1, node 2, or node 3. If you have 2 pods, 2 pods can be on a single node. It can be on 2 nodes. So there's actually no direct way the scheduler does it. But you can actually customize how you want it to work. So there's a way you can configure it to ensure that there are certain nodes you want your pods to deploy to. We call that node tainting and node affinity, where you configure your pod to deploy at a particular node or set of nodes. You don't want it to go outside that. Okay? The next thing we have here is a volume. A volume can be thought of as a directory which is accessible to the containers. Now, if you remember very well, during our Docker class, we talked about containers being stateless. That means they are not designed to store data, but time and time again, people are finding out better ways to actually make containers store data, and volumes came into play. So in Kubernetes, what the volume means is that it helps to maintain states, it helps to maintain data for you. And in the case of Kubernetes, you actually need to have a volume, okay, something like an EBS volume in your worker node. And it is in that particular place that is going to store those information. So with volumes in containers, it makes it possible for your containers to become stateful instead of just being stateless applications. The next we have here is secrets. Now, secrets can be defined as Kubernetes objects used to store sensitive data, such as username and passwords with encryption. So if you are working with, say, a third-party application like Facebook or like Google, they usually give you what you call an API key and an API secret. Okay, now in that scenario, what happens most times is that you need to be able to store those credentials in a secret place, not in your application code, but in somewhere that is secret, so that you can easily access them, okay, secretly. Now, the place where this can be done is using the Kubernetes secret. Although it just uses base64 to store the passwords, but it follows the 12-factor app principle, which states that you should not store credentials within your application code. It should actually be outside of your application code. So secrets is within the Kubernetes cluster, and if you configure secrets properly, they can actually work with environment variables, which your application can actually connect to and receive parameters from. So that's the job of secrets. The next is what we call a job. A job is a supervisor for pods carrying out batch processes. That is, a process that runs for a certain time to completion, for example, a calculation or a backup operation. So Kubernetes is not just built for APIs applications. It can also be used for building background processes and background jobs. And they can, if you configure a Kubernetes to be a kind of job, it means that it's going to run it something like a cron job on a schedule. And when it's done, it will end that particular process.
I have a question.
Okay, go ahead.
In last part, you explained secret. I need to know what is this outside place where we store our credentials and with encryption. What is that outside? It's a different container or within the container if it's out of the application.
It's actually in etcd.
It's an ATCD.
Yes.
Okay. So basically, it's in master.
Yes.
Okay.
Any other question? All right. So I assume that we are okay. All right. So the next thing we'll talk about is administering your cluster. Now, administering your cluster simply means managing the cluster, deploying applications, monitoring deployed applications, designing and implementing high availability functionalities in the cluster, and any other operations that has to do with working with the cluster. The CLI tool generally used for administering a Kubernetes cluster is called the kubectl command.
Okay.
Now, the kubectl command is used to create, update, view, and delete any kind of Kubernetes object or resource. The commands are constructed in a manner in which it is needed to get the desired results. To create a namespace, you can use the command kubectl create namespace staging. So this is an example of how the command works. kubectl create namespace staging. So the namespace you are creating is actually called staging. It could actually also be kubectl create namespace production, kubectl create namespace dev, kubectl create namespace test. Okay.
Okay.
So with that, we're able to generate a syntax that can help us to be able to write more Kubernetes kubectl commands without having to, cram it or go for documentations. So with that, the general syntax for kubectl commands is as follows: kubectl, operation, resource, and then other flags. So where operation could be create, view, delete, get, describe, and apply. You get that?
Okay.
And then where the resource could be the namespace, a pod, a deployment, a service, or replica. So can anybody just form a command for me, maybe say it out or just send it on the chat? Let's see how we can use the syntax to create a kubectl command. Yeah, thank you very much. Okay, anyone, any other command? Okay, all right. Thank you very much. So it means that we are getting into the grind. It's pretty straightforward. The commands are pretty straightforward. So this is what we'll be doing. I mean, hopefully from next week, we'll be doing a lot of kubectl commands, create, delete, update, change a lot of things. But it doesn't just end there. The first thing before we can start administering our cluster is the configuration file. Now, the configuration file contains authentication and authorization credentials that gives you access to administer the cluster with the kubectl command. Without the kubeconfig, any command issued to the Kubernetes API, be it via the CLI or API at all, will return an authorization failure. The kubeconfig is generated whenever a new cluster is generated or created, and usually resides in the kube.kube/config directory. So Kubernetes stores that config file in that particular directory. So what you need to do is to do kube, when you do kubectl config view, you see the configuration file. So whether you are setting up Kubernetes with say Minikube, okay, or with any other Kubernetes setup, or even EKS, within that machine where you are setting up the cluster, Kubernetes generates this configuration file and dumps it in this directory. And kubectl command automatically fetches for that configuration within that directory to be able to communicate with the cluster. If anything is missing in that file or anything is wrongly written, it's going to give you an authorization failure. So this is more or less the username and password that gives you access to be able to communicate and send requests to the Kubernetes cluster. Now, don't forget, your kubectl communicates with the Kubernetes API at the end of the day. So every request that comes to Kubernetes must come via the API. It doesn't request from anywhere. So the kubeconfig is more or less the, like I said, username and password, or the configuration that gives you access to administer the cluster. So it's a very important file. Now, apart from being able to manage your Kubernetes cluster using the kubectl command, there's another way of managing your cluster in a more repeatable form. Okay. And we know this is the time of infrastructure as code and all that. So Kubernetes is not left out in that. So the Kubernetes manifest file is a file that makes it easy to codify Kubernetes resources and their behaviors. The manifest file contains configuration instructions on how the resources are to set up and deployed into the cluster. The manifest file makes deployments easy to store, track, and make changes to, most especially when they are stored in a version control service. Now, the Kubernetes manifest file is written in YAML, yet another markup language, or YAML int markup language. So basically, we are saying that if you're actually working with a production-grade Kubernetes cluster, you might not really be doing everything with these commands, okay? You want to create a pod, you use the command. You want to create, you use the kubectl command in combination with the manifest file, because I mean, the real Kubernetes deployments, they have lots of configurations, okay? The secrets, okay, the config map, the environment variables, the name of the pod, the name of the deployment, the name of the image, which your kubectl command cannot take, okay? So instead of that, you have to write a YAML script, that serves as a configuration file for your application. And then you use the kubectl to actually administer and apply that file into your cluster. And then the configuration and that pod is created. Now, one advantage of using the manifest file a lot is that it makes your configuration repeatable and codified. So if someone else is going to deploy that same application in another cluster, the person doesn't need to ask you a lot of questions. The person can take that manifest file and deploy just the way it was written. So it makes it very flexible. And the beautiful thing is that it can also stay within repositories, which makes it very awesome. So you can actually decide that you want to keep your manifest files in a Git repository, and any other person can actually pull, make changes, and also pull and properly collaborate within that file. So everything we talked about in Git can also be applied into a Kubernetes manifest file. You could do things like pull requests, things like code reviews, to ensure that the manifest file configuration is up to standard and exactly what you need for that work that needs to be done. Am I making sense? Hello, are we there?
Yes.
So this is sample Kubernetes manifest file. This is how it looks like. So the first thing, it starts with the API version. Then it goes to kind. So you can see the kind I was talking about. This is a pod. The metadata name, more or less the name. And then the specification. So that's where we specify the containers. We have just one. We are doing, the name of the container is Nginx and the image is an Nginx image. So what this file will simply do is just to deploy an Nginx pod within the cluster. Are we clear?
Yes.
So this is a sample manifest file in YAML. A typical application contains lots of YAML files or a single YAML file and lots of configurations for different resources. Okay, that's all. Do we have any questions, feedback? If we're fine, then I will invite us to close the class today with setting up your own Kubernetes cluster. Then from the next class, we can start doing some work around that. So do we have, I would suggest that we do Ubuntu. I think this is a tool also like, it's a single node lightweight Kubernetes cluster, as you can see. I'm sure you can see my screen. So, I mean, it makes your setting up of Kubernetes for practice very, very straightforward. They used to have their command here in the home page. Okay, yeah, that's it. So if you are using Ubuntu, just say snap sudo install microk8 classic, and it's going to install it. So I will suggest that we get an Ubuntu 18 or 16, and just install microk8. Is it something we can do now, or want to do it against the next class?
Okay.
Which one? What do we think? Which